Welcome to today's paper reading. Today's paper is titled, Grandmaster-Level Chess Without Search. This paper was published on the AR14 preprint by Anian, Ruoss and colleagues from Google DeepMind. The abstract provides a comprehensive overview of the experimental evaluation conducted in the study. For the main experiments in sections 3.1 and 3.2, the same parameter settings were used. However, for the scaling behavior investigation and all ablations in sections 3.3 and 3.4, a different set of default settings was employed, focusing on computational efficiency and representative results. These details are fully provided in Appendix 8.2 and 8.3. The study also compares the puzzle performance of the 270M parameter model against Stockfish 16, GPT 3.5 Turbo Instruct, and AlphaZero's value network, using a large set of 10,000 puzzles grouped by their yellow difficulty. Stockfish 16 outperformed all other models, with the 270M model following closely. Additionally, the scaling analysis revealed that puzzle accuracy correlates well with overall playing strength, with larger models and datasets generally leading to higher performance, although overfitting can occur with small datasets. Figure 1 illustrates the process of data annotation and policy training for chess. At the top, all boards from randomly drawn games on Lichess are extracted, duplicates are discarded, and state values are computed using Stockfish. Action values and the best actions for all legal moves are also calculated. On the bottom left, training and test sets of various sizes are constructed, with the largest training set containing 15.3 billion action values. The test set includes 14.7% of boards that overlap with the training set, mostly early game states. Additionally, a test set of 10,000 chess puzzles with correct move sequences is used. On the bottom right, predictors are trained on 3 targets: state values, action values, or oracle actions, each forming a basis for a chess policy. The value predictors are discrete classifiers that predict the bin into which the oracle value falls. Table 1 provides a comprehensive comparison of the prediction and playing strength of our transformer models of varying sizes, 9M, 136M, 270M, against established chess engines like Stockfish 16, different configurations of AlphaZero, and GPT 3.5 Turbo Instruct. The table highlights the internal tournament ELO ratings, which are derived from the models playing against each other, and the external Lichess ELO ratings, which are obtained from playing against human opponents and bots on the Lichess platform. Notably, Stockfish 16, set with a time limit of 50 milliseconds per move, serves as the oracle for data generation, achieving a perfect Kendall's tau of 1 and 100% action accuracy. The models utilizing PGN format have access to the full move history, whereas those using FEN format only receive limited historical information. The best results among models without search capabilities are highlighted in bold. Table 2 summarizes the results of various ablations conducted on different parameters, as detailed in section 3.4. The action value predictor demonstrates superior performance in terms of action ranking, as measured by Kendall's tau, as well as in action and puzzle accuracy. The impact of varying the number of bins used for state and action value discretization shows that more bins lead to improved performance, indicating a balance between performance and computational efficiency. Additionally, the comparison of loss functions reveals that log loss outperforms L2 loss on 2 out of the 3 metrics evaluated. Figure 2 compares the puzzle-solving abilities of our 270M parameter transformer model against Stockfish 16, AlphaZero's value network, and GPT 3.5 Turbo Instruct using a dataset of 10,000 Lichess puzzles categorized by difficulty. Stockfish 16 performs the best across all difficulty levels, followed by our 270M model. AlphaZero's value network and GPT 3.5 Turbo Instruct show non-trivial performance but significantly lag behind our model. The comparison highlights the effectiveness of our model in solving chess puzzles, which relies on accurate value estimates rather than explicit planning. Figure 3 illustrates the puzzle accuracy across various training set sizes and model sizes, color-coded for clarity. The data shows that larger models trained on more extensive datasets generally achieve higher accuracy, which strongly correlates with both test set performance and overall chess playing strength. This trend underscores the critical role of scale in achieving strong chess play. Notably, the effect cannot be attributed to memorization, as less than 1.41% of the initial puzzle board states are present in the training set. However, if the model size becomes disproportionately large relative to the training set size, it can impede learning and lead to overfitting. The introduction of this paper highlights recent innovations in chess AI driven by large language models. Key advancements include the use of language-based models for chess, such as Canlish's work, and the encoding of chess games through natural language. Additionally, the paper discusses the evaluation of large language models' ability to play chess. Performance enhancements in chess AI are also noted, with strategic input representations and value loss enhancements significantly boosting the performance of vision transformers. The inclusion of chess-specific data sources and language model training has been shown to improve chess performance. The paper also emphasizes the importance of model and dataset scale, resonating with Stockle's exploration of scaling effects on chess performance. Figure 4 illustrates the bot's dilemma in choosing between two winning moves, nh6+, mate in 3, and nd6+, mate in 5. Despite nh6+ being the quickest way to win, the bot opts for nd6+ due to both moves mapping to the highest value bin. This scenario highlights the bot's inability to commit to a single winning strategy, potentially leading to random strategy alternations and increased risk of drawing or losing the game due to minor errors. The board shown is from a game between a 9M transformer, white, and a human player with a blitz yellow of 2145. In the experimental setup, the tokenization process ensures a consistent representation of the chess board. Each board position is encoded into 64 characters, with additional tokens for the active player and castling availability. The main setup involves training for 20 million steps with a batch size of 4096, covering approximately 5.35 epochs. The model architecture is varied to optimize performance, with the goal of achieving strong chess capabilities through standard supervised training and generalization to unseen board states. In this experiment, the Atom Optimizer is employed with a learning rate of 1 × 10⁻⁴, as described by Kingma and Ba in 2015. The training dataset consists of 10 million games, which are used to develop the action value policy with 128 return buckets. Additionally, a Stockfish time limit of 0.05 seconds is applied, and the unique sampler along with Polyak averaging techniques are utilized to enhance the training process. In this section, the authors discuss the evaluation method used, which involves evaluating the model on 1,000 games and 1,000 puzzles from a different month than the one used for training. The model architecture employed is a vanilla decoder-only transformer without causal masking, as described by Vaswani et al. In 2017. While the text mentions improvements, specific details are not provided, focusing instead on the evaluation process and training details. In this study, the authors adopted the Llama architecture, which includes post-normalization and the SWIGLU activation function as proposed by Tuvrin et al. In 2023. 3 different model configurations were used, the first with 8 attention heads, 8 layers, and an embedding dimension of 256, the second with 8 heads, 8 layers, and an embedding dimension of 1024, and the third with 8 heads, 16 layers, and an embedding dimension of 1024. The varying embedding dimensions of 256 and 1024 were explored to assess their impact on model performance. Thank you for watching.